Hi guys, we're going to talk about calorimetry today. Calorimetry is a lab method in order to determine the heat that is transferred by my reaction or by a system indirectly. So we learned that if I want to calculate the heat that is transferred, I do Q equals MC delta T. Now that sometimes is a little bit hard to do. Some reactions are, just hard to calculate these things for, especially that C. And do you put it in for the reactants or the products or a combination of both? So it gets kind of complicated. So we use calorimetry, and calorimetry relies on the idea of the law of conservation of energy. So energy can't be lost or destroyed. It has to transfer from one place to another. And so the idea is whatever I'm studying is my system. Usually what I'm studying is a chemical reaction. So my system has surroundings. And so if it's an exothermic system, if my reaction itself is exothermic, it's going to release energy to the surroundings. So if Q of my system, let's say, is negative 5 kilojoules, negative, remember, means just it's exothermic, it's releasing energy, then Q of my surroundings is going to be positive 5 kilojoules, right? So my system releases 5 kilojoules, my surroundings absorb that 5 kilojoules. The negative means it's releasing, positive means it's absorbing. What if it's the opposite? So what if it's endothermic? So endothermic means the system is absorbing energy, so we're taking energy from the surroundings, giving it to the system. So let's say Q of my system is positive 8 kilojoules because it's absorbing, so that's why it's positive. That means Q of my surroundings is negative 8 kilojoules because the surroundings are releasing energy to the system. So the idea of the law of conservation of energy basically says that one releases, the other one absorbs, and so we get this equation from that. Q of system is equal to negative Q of the surroundings. Your system could be anything, whatever you're studying. Most of the time as chemists, our system is a chemical reaction. And so usually we use Q for heat. Like let's say I'm heating up some water to make a cup of coffee or something like that, then I use Q. When I'm talking about a chemical reaction, usually I use delta H or enthalpy. So delta H means the same thing as Q. Is just typically used when I have a reaction as opposed to, just a physical process. So my Q of system, sometimes I call that delta H of the reaction. And so this equation is the same thing. Basically, delta H of the reaction, or which is Q of system, is equal to negative Q of surroundings. Okay. Now, calorimetry relies on that. And so let's say I have some magnesium. I'm going to put it in HCl. Now I know that that's an exothermic process, right? Get MgCl2 and H2. And it's delta H of this reaction is exothermic, it's negative, right? But how do I calculate that using Q equals MC delta T? I really can't. So that's where I rely on calorimetry. There are two types of calorimeters. There's the coffee cup calorimeter, which is this one, and then something called a bomb calorimeter, which we'll talk about in a minute. So this is the coffee cup calorimeter. It's basically a cup that is insulated, or a vessel that is insulated. In our labs, we used 2 styrofoam cups, and then another half of a styrofoam cup as a lid. So it's basically a vessel that is insulated and covered, and there is a hole for a thermometer in it. So the idea here is that I can do this reaction in water or in a solution. So my HCl, remember HCl is a gas at room temperature, so this HCl is a solution, it's aqueous. So in our lab last year, we did this lab where we took the HCl solution here, we masked it, and then we put it in the calorimeter. We measured the initial temperature. We masked the magnesium by itself, and then we added it to the solution. and we made sure it's covered. We stirred with the thermometer and watched the temperature. And in this case, because it's exothermic, the temperature went up. And so we watch the temperature keep rising, rising, rising. The highest temperature we record down. If it was endothermic, then the temperature will go down. The lowest temperature is what we record. So then we say that the heat that's released by my reaction happening, my magnesium and my HCl particles reacting together, is absorbed by my surroundings. Well, what are my surroundings? Because theoretically, this is insulated, right? So what are my surroundings in this case? It's a solution or water, right? This stuff is dissolved in. And so I can say that delta H of my reaction, which is, again, the same thing as Q of my reaction, is equal to Q of the surrounding. My surroundings is a solution or water, right? And so the reaction is MC delta T for my solution, right? Q of the solution is MC delta T of the solution. Because I can very easily mass my solution, I can find the C for my solution. It's probably going to be pretty close to water. And I can find the initial and final temperature of my solution. So basically, I'm calculating how much heat is absorbed by my solution, and I'm saying this is the same amount of heat that is released by my reaction. So if I were, for this example, if I just do MC delta T for the solution, it's going to be a positive value because my solution is absorbing energy, right? If I put that negative, that makes it the delta H of the reaction, because then it's exothermic. My reaction is giving off that energy. My water or solution is absorbing that energy. So that's usually what we use in calorimetry if we're doing our reaction in solution. Just a side note, we can also split up both sides into MC delta T. So I can say, I'm going to write it here, MC delta T for my system is equal to negative MC delta T for my solution or surroundings or whatever the surroundings are. I'm actually going to say surroundings in general. When would I use this one? That's if I take like a piece of copper, like a hot copper penny, and put it in water, and I want to calculate like C or M or something like that for my system. We did this last year with the hot copper penny lab. So you use this one where you break both of them up when you are solving for M or C or one of the temperatures. You use this one when you are solving for delta H, which is Q of your system. Okay, so let's try a problem. It says 100 milliliters of 1 molar NaOH and 200 milliliters of 1.75 molar HCl are mixed. A change in temperature occurs. Both solutions have an original temperature. It's given to us. They also give us the final temperature. It looks like it went up. They give us the density is 1 gram per milliliter, so just like water. Specific heat capacity, they give that to us. It's pretty close to water. And they want us to calculate the change in enthalpy during the reaction. Now notice I started reading those numbers and then they confused me. So I just kind of like said, oh, I have a initial temperature, I have a final temperature. Sometimes that helps. It's a little tip that I use. I don't focus on numbers because they distract me a little bit. I say, oh, I'm given a volume and molarity, temperature, and I use words as opposed to numbers when I'm thinking of the problem in my brain. So what's happening here? I'm taking 100 mils of the NaOH, and I'm adding to that 200 mils of my HCl, and they mix together, and then the temperature increases, and I want to find, what do I want to find? I want the enthalpy during the reaction, the enthalpy of the reaction. So I'm looking for delta H of my reaction. So when I'm reading this, I say, oh, it looks like I'm having a reaction in a solution. So I think to myself, oh, Q of system equals negative Q of surroundings. And then I say, oh, my system is this chemical reaction. So that's Q of my system here. What are my surroundings? My surroundings in this case looks like it's a solution. We're doing this reaction in solution, right? So Q of solution. So once I figure out it's a calorimetry problem, I write Q of system equals negative Q of surroundings. Then I identify my system. I identified that as a reaction. And my surroundings, I identified that as my solution. And then I think to myself, do I split up just my surrounding side into MC delta T, or do I split both of them up? Well, what am I solving for? I'm solving for the enthalpy, the delta H. So I want to keep that intact so I can solve for it. So then I say that is equal to negative MC delta T of my solution. So delta H of my reaction is negative MC delta T of the solution. So negative, what's the mass of my solution? Let's see, I have 100 mils and 200 mils, so that's a total of 300 mils total. And they tell us it's the density of water is 1 gram per milliliter, so 1 gram over 1 milliliter, so that tells me it's 300 grams. So 300 grams. Okay, C, they tell us is 4.19 joules per gram Celsius. And then delta T is final minus initial. Final is 31.3 Celsius. Initial is 24.6 Celsius. Now, if I were to plug this in just this part without the negative, that's going to be my MC delta T of solution, which is Q of solution. That should be positive, right? Because it's this reaction is exothermic, so that means giving off heat to my solution, so my solution is absorbing energy. Because I put that negative there, that makes it the delta H of the reaction, and it's going to be a negative value. So my delta H of the reaction ends up being negative 8,420 joules, which is consistent with it being exothermic because my temperature went up. Now, sometimes it's a little confusing. Sometimes they ask you, like, what is the enthalpy change or what is delta H? Sometimes they tell you how much heat is released. And so some students are confused whether they should use the negative or the positive because it says how much heat is released sometimes. And so whatever the question is asking, it's safe if you write it as the positive value and then write either absorbed or released after it. So that's what I would recommend if you're not sure whether you should use the positive or the negative. I would write it as a positive value and then write either released or absorbed. Now, if you write it as positive without writing released, it's not going to be correct, so be careful. But either answer is totally fine, either with the negative or with the word released. All right, so now let's look at a bomb calorimeter. They use bomb calorimeters when a reaction is not done in water, in a solution, and they use these to find the calories in food. So it's the same idea here, that Q of system is equal to negative Q of surroundings. So we're going to measure the heat that's released or absorbed by the surroundings and say that's equal to the heat transferred by my reaction. So the difference here is that the water is outside of the reaction. So there's this inner chamber, which we call the bomb, and that's where they put the reactants. So let's say I want to know how many calories are in a piece of apple. So what they do is they dehydrate the apple, and then they put it in here, and this is connected usually to oxygen or something like that. And then that chamber is surrounded by another chamber that has water in it with a thermometer, and then that is insulated from the outside. So what happens is they have these electrodes, supply electricity, and they also have oxygen available, and so they burn the piece of apple. As the piece of apple burns, then it gives off heat to the water, and it changes the temperature of the water. So I can do the same exact thing that I did before, except it's just in a different chamber. Now, in addition to the water absorbing that heat, the chamber itself, like the bomb calorimeter itself, will absorb some water, the walls of the calorimeter and so on. And so sometimes they'll give you information just about the water, like the mass and the C and the delta T for the water. Sometimes they'll give it to you for the water and the calorimeter, like the bomb calorimeter itself. And sometimes they'll just give it to you for the whole calorimeter, like they'll consider the calorimeter and the water one thing. But the idea is the same, that Q of my system is equal to negative Q of the surroundings. Sometimes the surrounding is water, sometimes the surroundings are the bomb calorimeter, sometimes the surroundings are the water and the bomb calorimeter. So how would you know? They'll tell you, like they'll tell you information about either water or the bomb or both. So if they give you both, you just say, well, then the surroundings are both water and the bomb. Bomb means bomb calorimeter. And so when you ID your system and surrounding, you say the system is my reaction. My surroundings are both the water and the bomb. Or one of them. Again, it depends on what they tell you. So let me show you an example, because we've never really done an example like that last year. So we have a 1 gram sample of octane, which is C8H18. It's burned in a bomb calorimeter, and they give us the mass of the water. They tell us the temperature of the water and the bomb, of both of them. Rise, and they give us the initial and the final temperature. They give us the heat capacity of the bomb, and they want us to calculate the total heat given off by the sample, and then the heat per mole evolved. So let's think about this. They say the word calorimeter in there, right? So automatically I think calorimetry problem, Q of system equals negative Q of surroundings. Then I ID, what is my system? What are my surroundings? Well, it looks like octane burning is my system. So you can write, delta H of octane. You can write just delta H of reaction. You can just write delta H. What are my surroundings? Well, it seems like they're talking about water. They're also talking about the bomb. So my surroundings is both water and the bomb. Right? So then I say, do I want to split both sides or just one side? Obviously, I'm looking for delta H of the reaction, so I'm just going to split this side up. So delta H of my reaction is equal to negative MC delta T for water and MC delta T for my bomb. And then I plug in my numbers. So put my negative here. Let's see, what's the mass of the water? It says 1.20 kilograms. I need that in grams, so 1,200 grams. We'll put a couple of brackets here. C for water, 4.184. They don't give it to you here. They would give it to you on the exam. Joules per gram Celsius. Delta T for water is final minus initial, so 33.20 Celsius minus 25.00 Celsius. All right. Sorry. There we go. That is MC delta T for my water. Then I'm also going to do MC delta T for my bomb. So M, do they give us the mass of the bomb? They don't. Do they give us C for the bomb? Yeah. So look at this. Do you see anything different here? So normal C, specific heat capacity, is usually in joules per gram Celsius, right? Look at the specific heat capacity of water. We're missing the grams. what happens is a lot of times when they give you information about the bomb, they'll give you the M and the C combined. How can you tell? Because of the units. So if I take the mass, which is in grams, and I multiply by the C, which is in joules per gram Celsius, my grams will cancel and I get joules per Celsius. So if they give it to you in joules per Celsius, that means M and C are together combined. So this number is both M and C for the bond. It's just to make it easier for you. It's not really to confuse you, it's just to make it easier. So 837 joules per Celsius, that is M and C for the bond. Delta T is the same, 33.20 minus 25.0. And then we calculate that. So that ends up being negative 48.0 kilojoules, or 48.0 kilojoules released. It is totally up to you whether you want to put it negative or say the word released, or given off, or evolved, whichever of these words. All right, we got this right here, which is the total heat given off by the sample. Let's look at the other part, what else they want. They want the heat per mole evolved. So what's the difference? They want heat again, so they still want delta H, but what's the difference between the heat per mole evolved versus the total heat given off? Well, when we calculated this, we used a specific amount of water and of what's in the calorimeter. So let's say I double my sample. Let's say I have 2 grams. Then I'd have double the heat released, right? And so, excuse me, this is the heat that's released for the 1 gram sample, because that 1 gram sample caused the temperature to rise this much. So I want it per mole, not for 1 gram, but for a whole mole of octane. So what do? If I want heat per mole, that means I divide by the moles, right? Because this is the heat per 1 gram. I want it the heat per 1 mole. So what I could do is I could change my grams to moles and then take my kilojoules, divide by it. So I'm going to do that on the side here. So I'm going to take 1 gram of C8H18, and I'm going to change that to moles. 1 mole is 114 grams. Now I'm going to calculate that. This gives us 0.00877 moles of octane. So then I say, again, you could do the positive or the negative if you want. I'll use the positive one with the divided by 0.00877. This gives me 5,470 kilojoules per mole released. Again, you can use the word released, or you can put a negative in front of that number. There's another way to do it using your units. So I'll show you the other way. Get a different color here. Kind of running out of room. I'm going to do it up here. So I got 48.0 kilojoules. And this is for 1.00 grams. So right now is kilojoules per gram. I wanted to say kilojoules per mole. So what you could do, you want to get rid of the grams, so put it here. You want it to say kilojoules per mole, so you put the moles here. And you could say 1 mole of the propane is 114 grams. That way your grams cancel, you end up with kilojoules per mole. So either way, both ways you'll get 5,470 kilojoules per mole released. Now, one more thing I want to mention is the difference between the just kilojoules versus kilojoules per mole. Let's say I ask you to do this reaction in the lab, and you all use different masses. So one of you uses 1 gram, the other one uses 1.5 grams, somebody else uses 1.2 grams. Because you're using different amounts, your temperature change is going to be different, and your delta H at the end will be different. So we are all going to have different amounts of heat released in kilojoules. But if we all then do this extra step where we divide it by the number of moles and get kilojoules per mole, we should all get the same value, excluding sources of error, of course. So if we all did it the same exact way, but used different amounts, it would still end up being the same value per mole. Because let's say one group uses the 1 gram and gets this, the other group uses 2 grams, they're going to get double this. So then when they take the heat, the doubled kilojoules and the doubled mass, they're going to end up with double the moles, and therefore you're doubling this number, you're doubling this number, and so it ends up being the same ratio and the same kilojoules per mole. And so when you look at any table where heat is listed, like heats of formation or something like that, in any of your tables, they're always going to be listed as kilojoules per mole. That way it's a value that everybody can use, and we know that that's for 1 mole. They will never just list kilojoules without the per mole. All right, that's it for calorimetry. See you guys later. Have a wonderful day.